Today we're going to talk about length contraction. Length contraction is another effect of special relativity, where at velocities approaching the speed of light, length appears to contract. So length appears to contract, that means to shrink, to reduce at velocities approaching the speed of light, and this occurs in order to compensate for time dilation, another of those effects of special relativity. Only the length in the direction of travel changes though. The height remains the same, the depth remains the same, it's only that dimension of space in the direction of travel, the direction that whatever craft or whatever object is travelling in. So just looking at an example, if some object or a spacecraft was travelling at 0.9 c, and it travelled a distance of 4.5 light years, 4.5 light years, that takes 5 years for an observer in Earth's reference frame. And it also takes 2.2 years from an observer aboard the craft. And that difference between 5 years and 2.2 years is due to the effect of time dilation. So if that was the same distance that the spacecraft appeared to be travelling at, and it took 2.2 years to travel 4.5 light years, the velocity you would appear to be travelling at is just velocity equals displacement over time equation. 4.5 light years divided by 2.2, 2 times the speed of light, 2c, and that is twice the speed of light. It violates the laws of physics. The speed of light is an absolute limit. And the reasons for that will become apparent in later videos. The magnitude of velocity must be the same for all observers as well. We can't have one observer appearing to be travelling or to see something travelling at 0.9 c and the velocity aboard the craft appear to be greater than that, much greater or different to that. The velocity of all parties in inertial reference frames needs to be the same. You can think about if you're in a car and you're driving along at 100 kilometres an hour, you see an observer on the side of the road, they see you travelling at 100 kilometres an hour too. And if you look out at that person, they appear to be travelling away from you at 100 kilometres an hour in the opposite direction. So the magnitude of velocity is the same. The direction of travel is negative. It's different. So although you might be travelling in this direction, the other person appears to you to be travelling in the opposite direction at 100 kilometres an hour. But the magnitude of velocity is the same. It remains the same for all observers in inertial reference frames. So velocity equals displacement over time, velocity equals length over time. So if we're in a rest reference frame relating to it, measuring relativistic time, we're measuring the rest length. We're looking at the rest length of whatever object it is, or whatever distance that we're talking about. If it's the distance between Earth and Rigel, the star Rigel, or the star Betelgeuse, or the star Antares, whatever, the length that we're measuring is the rest length. We're at rest. That length is at rest compared to us. And that velocity that we measure a craft travelling at is the same velocity that craft measures its velocity at. So, but the length that's involved here is going to be a relativistic length. The length that is aboard is different aboard that craft, and it's going to be aboard the craft we're going to be measuring proper time as well. So L0 is defined here as proper length or rest length. So the length of an object when it's at rest, or the length of the distance between two places at rest in the rest reference frame. And L is relativistic length. So if we were looking at a craft travelling past at a very high velocity, we would be measuring its relativistic length, not its rest length. Likewise, if a ship is moving and it's measuring the distance between two planets, it's going to be measuring the relativistic length, not the rest length, because it doesn't that distance, it doesn't appear at rest to the spacecraft, it appears like that distance is reduced. So the formula for calculating the relationship between relativistic length and rest length involves the Lorentz factor again, gamma here. So the relativistic length is equal to the rest length divided by the gamma, divided by the Lorentz factor, this gamma here. So that means that L is equal to L0 multiplied by the square root of 1 minus v squared on c squared. Just a note on distances. So the definition for 1 light year is the distance that light travels in a year. So 1 light year is a distance, so it's velocity times time. So here 1 year times the speed of light. So 1 year is 365 days multiplied by 24 hours multiplied by 60 minutes multiplied by 60 seconds multiplied by the speed of light, which is about 3 times 10 to the 8 metres per second. So that value is approximately 9.5 times 10 to the 15 metres. Very large distance, very, very large distance indeed. However, if you use the units of light years, you'll be able to and you've got velocities, a velocity in terms of c, in terms of the speed of light. The two will cancel out, and the units we'll have left over will be years. So if we're working in the time units of years, the velocity units with respect to c, and the distance units of light years, all of these units are mutually compatible. Just looking at 2 examples now. First one, determine the distance that a spacecraft travelling at 0.6 c would appear to travel in the spacecraft's reference frame if the distance in Earth's reference frame is 640 light years. So we're looking for the relativistic length that will be perceived by the spacecraft travelling at this velocity. So the velocity is 0.6 c, the rest length, the distance between these two, the distance that we're travelling, 640 light years there, and we're trying to look for the relativistic length. So we know relativistic length is L0 multiplied by square root of 1 minus v squared on c squared. L0 is 640 light years in this case, and our velocity is 0.6 times the speed of light. So we can cancel out 0.6 squared times c squared, which is the velocity squared, divided by c squared. The c squareds cancel out, and the 1 minus 0.6 squared is equal to 0.64. The square root of that multiplied by 640 light years is 512 light years. So we can see at that velocity there's a considerable difference in the distance that is measured by the spacecraft, around 138 light years less at that velocity, just over, or 0.6 c. Second example, we've got a character, Peter Wayland. He has 3 years to live, and to find a cure for his ailment, he must travel to a star system that is 5.5 light years away. And we need to find out at least how fast he needs to travel so that he reaches his destination before he dies. So pretty serious situation we've got going on here. He's got 3 years to live. So that's 3 years in his perspective. So if he's travelling on a spacecraft, that will be proper time we'll be measuring. So T0 will be 3 years. But the rest length that we've got, the distance that he actually has to traverse, is 5.5 light years. So that's not relativistic length. That is the length that we need to the rest length that we measure from Earth. So L0 is 5.5 light years and T0 is 3 years, and we need to find velocity. So we don't have a formula that has these variables ready to just plug in and go. So we need to maybe manipulate some of the equations that we know. So we know that the velocity that he's going to have to be travelling at is the relativistic length divided by proper time. So we can manipulate those, multiply both sides by T0, and we get L. Now we know L here, relativistic length, is equal to L0 divided by the gamma constant. So that's L0 multiplied by square root of 1 minus v squared on c squared. We go through some algebraic manipulation here. I'm not going to bore you with it, but once we get to the end, we can substitute in the value for T0, which is 3 years, and the value for our length, which is 5.5 light years. here, and we get a velocity of 0.88 c. So this is the minimum velocity that he has to travel at in order to traverse that 5.5 light years and take 3 years to do so. So that means the velocity needs to be greater than or equal to 0.88 c for Peter to survive.